So, draw a periodic table on your test document or your quiz document, a small one, all right? So, I learned this from my co-teacher, Ms. McGrain, who works with me. It's the festival season, and she will draw a snowman, all right? What do you think the snowman represents? Yes?
As when we go down the periodic table, the size, the radius of the electron increases.
The radius or the size of the atom increases. Is that right? And you know for a Bohr model how many rings you have to draw. Is that right? So as you go down, the number of rings increase, correct? So the snowman actually denotes the radius, all right? Let's give him a hat and all that, all right? When you go across a periodic table, all right, what happens? Do your number of circles change?
No.
They don't. But do they become tighter and tighter?
Yes.
Yes?
Yes.
And you should be able to explain why. Why does it become smaller and smaller in size? Yes.
Protons are more of an attraction on the electrons. So
While the electrons are being added to the same distance or the same energy level from the nucleus. Is that right? But the force of attraction increases. So radius increases, all right? Radius increases while going across it decreases. Now, we learned two other trends. They will ask you definitions. What is ionization energy? Anybody in class? What is ionization energy? You should memorize definitions. Why is it only Luke who's answering? Yes. From an atom in the gas state, energy required to take away or required to remove an electron from an atom in the gas state. That is your definition for ionization energy, and you should memorize definitions. So, smaller the size, more is the ionization energy, right? Because the electron is now closer to the nucleus. The pull on the electron is more, correct? So what is the pattern for the ionization energy? If you notice, it's the opposite of the radius. If radius decreases, ionization energy increases. And if radius increases, ionization energy decreases. Yes or no?
Yes.
All right. What is the, yes? Radius and ionization energy. Smaller the radius, more is the ionization energy. It's the opposite. Okay? Now, what is the next one we learned? We learned what is electron affinity. Anybody in class, what is the definition of electron affinity? Not Luke again, somebody else. What is it? You can read off. All right, so you can define in your own words the tendency to attract a pair of electrons in a bond. It's very important that you remember it's in a bond, because it's like a tug of war. When two atoms are bonded, it's a relative comparison. Does that make sense? If you are put it against me, who has more power? Isn't that how we play tug of war? Is that right?
Yes.
If you don't even put me against someone, can you find out my power? You know how powerful I am? So remember, which will be more powerful? Which will pull the electron pair more towards itself in a bond? The smaller the atom. If you notice, the trend is the same as ionization energy. It increases. The smaller the atom, the more the electron affinity. Bigger the atom, lesser the electron affinity. The pattern is it increases across and decreases down. Both ionization energy and electronegativity are the opposite of radius, right? But there is a catch when you do electron affinity. Put a star here, and what should you notice? Noble gases. Do they ever make bonds? No. All right? Noble gases have zero electronegativity. So if they give you 3 in a row, say I give you oxygen, fluorine, and neon. Are you looking up at the periodic table?
You know that neon's all three.
You know oxygen, fluorine, neon. You would write an arrow and say it increases. Which is the most? Which is the most among the 3? Oxygen, fluorine, neon. Electronegativity increases across a period. Which has most electronegativity? Better circle fluorine. Do not give me neon. Does that make sense? Do you understand it? Here is where kids will forget and circle the wrong answer. Alright? Whenever it's electron affinity, remember it's in a bond. And noble gases don't have it. Alright? Please remember that. The next thing we did was shielding. Did we talk about shielding in this class? So, more the circles, more the shields. Is that right? So how does shielding change as you go down the group? Shielding increases as you go down. Is that right? Shielding increases. But what is the shielding effect going across? The number of circles remain the same. Therefore, shielding is constant going across a period. Is that right? So if I compare the shielding effect of beryllium and boron, are they any different from each other? Beryllium and boron are across. Are they any different from each other? No. Do we understand shielding effect? And shielding effect is the underlying cause to explain trends. Is that right? I could ask a question, going down, the nuclear charge increases. Why doesn't the atomic radius decrease? As the number of protons increase, the atomic radius should decrease. Why doesn't it decrease going down the group? Because of shielding. Because of the inner core electrons that act as a shield, and hence the nucleus is not able to attract the valence electron. Yes or no?
Yes.
Do we understand this?
That's why
Yeah. Okay? It doesn't feel. The effective nuclear charge is reduced. Yes, that's the language. Okay? Are we good with trends so far? There is one more trend we will learn today. That is going to be electron affinity. Alright? Electron affinity has the same pattern. Look, ionization. Remember atomic radius. Wait, sorry. We did electronegativity. Ooh, this is wrong. I'm sorry. This is electronegativity. Sorry.
It's recorded on the
Electro. It's okay. I'm making a mistake. This is electronegativity.
So electronegativity.
Negativity is in a bond. Electronegativity is in a bond. Are we good? Did we make the correction? Yes. Electronegativity is in a bond. And noble gases, I wrote electronegativity here. Nobody corrected me while I was writing it. That is sad. That is sad. Electronegativity is in a bond. Today we are going to learn electron affinity, What is the difference between electronegativity and electron affinity? Electronegativity is in a bond. Electron affinity is the love for electron when the atom is by itself. Alright? How much? The energy released. What is electron affinity? Energy released when an atom, not in a bond, when an atom accepts an electron. Are we good? And in this case, energy is generally released. Energy is generally released in electron affinity. You require energy for ionization energy. Does that make sense? To remove, you require energy. But when you add, energy is released. You see the difference? Ionization energy is endothermic. Electron affinity is exothermic.
So the reverse.
They are the opposite of each other. But remember, there is only one trend you really need to know. Atomic radius. The snowman. Snowman increases going down, decreases going across. Every other trend is the opposite of snowman. That's easy to remember, right? Whether it's ionization energy, whether it's electronegativity, whether it's electron affinity, it is the opposite of radius. Shielding is constant, right? Going across. Shielding is constant going across. Is that right? But the catch to answering questions is to remember the exceptions. To remember the exceptions. You will write this pattern down. You'll remember everything is the opposite of radius. Is that easy? Now you have to remember exceptions. What was the first exception we hit? Electronegativity. Noble gases have zero electronegativity. Now we are going to get into more exceptions. Do you hear me? All right. So let's go to our extension notes. Let's go to our extension notes. All of you come to this extension note.
So,
Yes.
electronegativity is which
In a bond.
which one has the greater pull?
Which has a greater pull?
And then
Electron affinity is when the atom is by itself. If you add an electron to it, how much energy will it release?
so it's smaller.
The atom, the more energy it will release because it's closer to the nucleus.
Okay.
Wait, so what's the for electron affinity? When you go across it?
Yes, when you go down it decreases. Because the bigger the atom, you're adding it far away from the nucleus, it will release less energy. The closer you add to the nucleus, the more energy it's going to release. Does that make sense?
Does that make francium the most reactive element?
Francium is a very reactive element. Okay, listen up. Listen up. Whenever you define radius, can you tell me that radius is from the center of the nucleus to the outermost edge? Can you ever define radius like that?
No.
If you give me it's from the center of the nucleus to the outermost edge, as you have learned it in geometry, I will mark you wrong. Why? Because it's an electron cloud. I do not know the edge. Yes or no? Do I know the edge of a cloud? So you should always tell me radius is half, 1/2 the distance between two neighboring nuclei. Do you understand that? All right? Why are two nuclei needed? Because it's a cloud. You really don't know where it ends. Okay? What is shielding effect? What is the definition of shielding effect? You can write it in your own words. All right? The inner core electrons, reduce the attraction of the nucleus for the valence electron. This is known as shielding effect. This is known as shielding effect. And the nuclear charge that the valence electron actually feels is known as effective nuclear charge. The new nuclear charge that the valence electron feels as a result of shielding is known as the effective nuclear charge. Yes or no? Do you understand it? Now, shielding effect increases going down a group and stays the same across a period. Right? Everybody understands that? I think you're going to complain about my handwriting, but are you actually processing the information in your head? Yes or no? Does it increase going down? Does it stay the same across the period? Everybody good? Okay. Now, if you think about the atom, there are actually only two forces. The nucleus is positive, the electron is negative. So when one overpowers the other, you see the size increase, decrease, which in turn results in the change in ionization energy, electron affinity, electronegativity, and all that. Is that right? Right? Just but one force. Positive attracts negative, negatives and negatives repel each other. That's the only two kinds of forces. What happens to the nuclear charge as we go across a period? The number of positives increase. What happens to the core or the shielding electrons? They stay the same. Stay the same. What about the energy level to which you are adding one more electron? That stays the same. All right? Stays the same. So what is the net effect? This is same, but the positive increases. So what happens to the radius? It decreases. Yes or no? These are the reasonings or the, when you are asked to explain, this is what you will use, right? To explain. Going down the group, the nuclear charge again increases. Hey, going down. This is going down. This is going across. Going down, the nuclear charge still increases. But what about the core electrons? They also increase. What about the energy level to which you are adding the electron? You are increasing that. It's further away from the nucleus. So these two increase, overpower this increase. Yes or no? Yes or no? The core electrons and the distance from the nucleus overpowers the increase, in the nuclear attraction. So what do you see happen to the size? Increases. Right? Yes or no? So these are the reasons you will use to explain the whys when you get asked. Do you understand it? Okay. Can I move on? Can I move on? Okay. Let's move on. So now you will get asked, oh, I forget to do this on your warm-up. Okay? I forget to do this. Draw a small periodic table, all right? And always, 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 which side is the metals? To the left are the metals. And metals like to lose or gain? Lose electrons. When they lose electrons, what do they become? Positive ions, which are called what? Which are called cations. And what happens to the size when they lose an electron? It becomes bigger or smaller? Smaller. Is it not writing? All right? It becomes Okay?
Really,
Becomes smaller. Complete the other side. Complete the other side by yourself.
What?
Is that asking too much, Sanjay?
No, we were supposed to
Another side.
What?
What about the non-metals?
Oh.
What about the non-metals? What do they make? Non-metals make,
Onions.
they gain electrons, they become negative, they make anions, and they get bigger. This is basic understanding, right? What is it? Are you okay? Okay. All right, now, so if they ask you to compare the size of Na and Na plus, so you should be able to draw and explain, all right? You should be able to explain. Sodium has 3 energy levels. Yes or no? 3 rings. Total of 11 electrons, correct? When sodium becomes sodium plus, does it like to lose that 1 electron to get to 8 on the inside? So what happens to the size? It becomes smaller. You can explain it by saying how many protons are in the middle. 11 protons. It's not getting aligned properly at all. It's a. Okay, I'm going to write it in the bottom here. All right. In the nucleus, there are 11 protons. How many surrounding electrons? 11 electrons. Is that right? But then, when you come to Na plus, how many protons? 10, 11 protons, 11 protons, and how many electrons? 10 electrons. More protons attracting lesser number of electrons, is the pull going to be more? Is the size going to be smaller? Do you understand it? So, what about an anion? Why is an anion bigger in size than the neutral atom? So, if you take F and F minus, how will you explain it? Fluorine has how many protons? 9 protons. It's attracting 9 electrons. Is that right? Now you are adding an electron. Do you have to expand the ring to accommodate the incoming? And don't they already repel each other also? Yes or no? They hate each other. Don't they want more space between them? Yes or no? So, this is 9 protons, but how many electrons? 10 electrons. The incoming electron is repelled by other electrons, so the cloud expands. 9 protons cannot attract 10 electrons as much as 9 protons can attract 9 electrons. Is that right? This results in an increase in the size of the anion. Yes.
What about with like elements in the center of the periodic table, like iron? Would they still get smaller?
Iron and F block, I will not dwell into it too much because now you're going into the D and the F orbital, and the shielding from the nucleus is not that effective, so it makes a big difference in how their size plays out, and we are not going to go into that. You will hit that in AP Chem, all right? Now, we need to know, you will get asked questions when you compare isoelectronic ions. Remember what are isoelectronic ions and atoms? Meaning, iso means what? Same number of electrons. Alright? So, let's compare 3 of these. Iso meaning they all have how many electrons? 10 electrons, 10 electrons, 10 electrons. Which will be the biggest? Which will be the smallest? And why? Because how many protons are attracting how many electrons? 9 is attracting 10. 10 protons are attracting 10 electrons. 11 protons are attracting 10 electrons? Yes or no? In which case will the pull be more? When the number of protons are more. Therefore, this will be the smallest in size and this will be your biggest in size. More the number of protons will cause the more attraction and the size to decrease. Do we understand this? Okay, let's move on and let's do ionization energy. Okay, ionization energy, energy required to remove the outermost electron. Is that right? What does a neutral atom become when you remove the electron? It becomes a cation. It becomes a +1 ion. Is that right? What is the second ionization energy? When from the first one, you are removing one more electron. Now in this case, 10 magnesium is 12. 12 protons were attracting 12 electrons. Is that right? But in this case, 12 protons are attracting 11 electrons. Yes or no? The pull is more. When the pull is more, the second ionization energy, you will need more energy to pull the electron out. Yes or no? So, proton to electron ratio is increasing, less and less negative charge to attract. Therefore, the electrons are pulled in tighter, which means you require more energy to pull the second electron out. Yes or no? Therefore, the second ionization energy is more than the first ionization energy. If you are not able to write with me, I will post a PDF document of this, typed up and everything. Is that okay? If you don't understand, stop and ask. The most important thing is you understand. Now, moving on, let's look at this table. All right? Let's look at this table. Now, notice this is the first ionization energy. That is the second ionization energy. And this is like 500. It is almost triple. Is that right? From 700 to 1400 maybe has doubled. Is that right? But between 1400 and 7000, it's become almost 7 times. Yes or no? This is really, the jump is really high. That's the third ionization energy jump is really high. If I take aluminum, the first to second to third, there is a gradual increase, but then between the third and the fourth, there is a steep increase. Yes or no? If I take silicon, first to second to third to fourth ionization energy, there is a gradual increase and then suddenly it spikes. Why is there a sudden spike in the first, in the second, in the third, in the fourth, and the fifth, and so on? You should know the reason and you should be able to explain why. Let's look at sodium. Sodium has 3 valence electrons. 3 rings. How many valence electrons? 1 valence electron. Yes or no? You remove the first electron, that is your first ionization energy. Correct? Where are you going to remove the second electron? Are you digging into a lower energy level that is closer to the nucleus? Therefore, you see a sudden jump. Do you understand it? Let's look at magnesium. If you look at magnesium, magnesium has how many valence electrons? How many valence electrons? 2. I remove the first one, that's my first ionization energy. Is that right? I remove the second one, that is my second ionization energy. Where am I reaching into for my third? This is my third. Am I going into an energy level that is closer to the nucleus and hence is pulled more? That's why I see the sudden jump between the second and the third for magnesium. Where will you see it in aluminum? Aluminum has 3 valence electrons. So going between the third and the fourth is when I go into an inner energy level. Yes or no? Do we understand this? Do we follow this? Sanjay? Let's look at silicons. Let's look at, go back to magnesium. I think he just zoned out. Magnesium has how many valence electrons? How do you know how many valence electrons an element has?
Oh, by the
Number on the top, right? The dot structure, the Lewis dot structure. Does magnesium have 2?
yes.
So you remove the first one, that is the energy. You remove the second one, that is the energy.
We're removing electrons.
We are removing electrons. It's ionization energy. We are removing electrons. When you're trying to remove the third one, where is the third one? Is it in an inner shell? Is it in an inner shell? Is that inner shell closer to the nucleus?
Yes.
Is it being pulled more?
The attraction.
It's more. The closer it is, the more is the attraction. Therefore, you see a sudden jump. Wait. You need to keep your head here. If it wanders, you won't understand. All right? Now, let's move on. Yes. I don't think you can remove that. The pull is so much that first, second, third, fourth, fifth, sixth, seventh. It's a gradual increase. They're all in the same shell. What? That's like you won't, it's impossible to remove all the 8 electrons. The pull will be so much, all right?
Is it really constant?
Not, where is it constant? Gradually increases. Yes, Pathian.
Sulfur is 27 out.
Yeah, the jump is, how many valence electrons does sulfur have? So where should you see the jump? From the 6th to the 7th. 1, 2, 3, 4, 5, 6. Do you see the sudden jump? Make sense? Okay, let's move on. Here is where you start learning exceptions. Let's learn exceptions, all right? Let's see. Okay. In the past years, I've made my students draw ionization energy graphs. All right? So if you draw an ionization energy graph, this is period 1. This is period 1, meaning this is hydrogen and that is helium. Going across a period, ionization energy increases. Going down a group, it decreases. So it drops. Between helium and lithium, it drops. And then going up, period 2. What is this? This is period 2. Period 2 goes from lithium all the way up to helium. Yes or no? I mean neon. Helium to neon, right? If you go to period 3, it goes from sodium to argon. Yes or no?
Ms.Geeta, I thought the noble gases don't have ionization energy.
They don't have electronegativity because they don't make a bond. You can pull the electron out. He just asked, argon, where is the 8th electron not being removed? You can pull electrons out. Okay. Are you listening? Are you listening?
Yes.
Thomas, Jeremy, do I have your head here? Now, Look at this. Ionization energy is supposed to increase going across a period. What element is this? This is beryllium and this is boron. It drops. Alright? After boron, this is carbon and then it's nitrogen and oxygen. It drops here. It drops here. You see that? When you go across period 3, this is magnesium and this is aluminum and it drops. After aluminum, this is silicon. It's phosphorus and sulfur and it drops. Why? Why does it drop between beryllium and boron? Why does it drop between nitrogen and oxygen? Alright? Now please listen. Here is where kids will make a mistake. When I ask you to arrange the elements by increasing ionization energy, are you listening? I will list lithium, beryllium, boron, carbon. They will draw on their periodic table. Ionization energy increases. And they will say lithium is less than beryllium, is less than boron, is less than carbon. Did they get the order right? No, there is a flip. Is that right? It is boron and then it is beryllium and then it is carbon. What, Hannah? Did I do it right or wrong? Is it lithium is less than boron, is less than beryllium, is less than carbon? Yes or no? The graph is giving me the answer. You will not have this graph on the day of your test. Right? Okay, let's go to the Y. Are you listening? Let's go to the Y. Now, we often think or draw only Bohr models. The Bohr model is wrong. We already said that, right? So, if you look at beryllium, the electron configuration is 2s2. If you look at boron, the electron configuration is 2s2, 2p1. Right? So, what do you know about the size of the s orbital? The s orbital is a sphere. What do you know about the p orbital? It's a dumbbell. Yes or no? Now, when you put the one electron for boron in the p orbital, isn't the s like spread out? It's all around the nucleus, right? But the p is in a narrow region, right? So the s acts like a shield. It's a very small shielding effect. Even though we say shielding remains constant, moving between the s and the s slightly shields the p. When s shields the p, what about the ionization energy? It's not getting pulled, right? So it drops. Does that make sense? Yes.
Why is there a decrease?
That is the next reason. All right? Is everybody able to understand this? Okay, let's go over it again. Beryllium has 2s2 electron configuration. Boron has 2s2, 2p1. The S is a sphere, right? When the sphere like completely encloses the nucleus. Yes or no? When you add it to the P level, which is a dumbbell, the S actually shields the P electron from getting attracted by the nucleus. And therefore, to remove the first one, it drops. Does that make sense? But then, as you go on to carbon, what happens? This positive really increases. The small shielding is not that effective. So it continues to increase.
So it's only reactive.
Only between the S and the P, you see a slight drop.
So like magnesium and aluminum too.
Magnesium and aluminum too. The same way. Going between the S and the P, you see a small drop. You understand? Yes, Kaira.
So there was also a drop between nitrogen and
Yes, that is the different reason. Did everybody understand the reason for the drop between beryllium and boron and magnesium and aluminum? The S shields the P slightly. Alright? Now, let's go to the next one. There is a drop between nitrogen and oxygen. Let's look at nitrogen's electron configuration. Is it 2p3? Is nitrogen 2p3? What is oxygen? 2p4. Now, these 3p orbitals are along the x, y, and z axis, and there is one electron in each, and they're spinning around the nucleus.
So when they repel each other.
Now, when you add one more electron, do you think the other electron likes the incoming electron? It hates it, right? They repel. So when you add the next electron, they repel each other. They hate each other. And so, if somebody is trying to remove this, it's like, take it away. I don't want it. Does that make sense? So, this electron, there is an electron-electron repulsion that makes it easier to remove the electron from oxygen. Do you think it's easy to remove it from nitrogen? Nitrogen is also half-filled. Don't they love their half-filled stability? All right? Yes, Luke.
How come that doesn't come true also when you add even more electrons? Like when you add more electrons.
The nucleus becomes more and more powerful in the center. Now this starts to take control. This becomes the overpowering force. It's a balance always between, it's a struggle, power struggle between the two all the time. And that plays out. All right? Do we understand this? So the reason between beryllium and boron is the shielding of S. The reason between nitrogen and oxygen is the electron-electron repulsion and the stability of the half-filled orbital. Do we understand? The reasons are not the same. Do not get them mixed up. Make sure you study them, because I definitely will ask one of these two questions on my test.
Well,
Is that clear?
Will this second rule be true to all the?
Phosphorus and sulfur too.
How about like?
As I said, we are not going lower down because there are other factors that play. Okay? Are we good with the exceptions? Not only do you have to know the reason, again, if I ask you to order them by increasing ionization energy, and I give you carbon, nitrogen, oxygen, what is the order? Carbon, nitrogen, oxygen, what will the order be? Carbon, oxygen, nitrogen. Do you understand? That's where kids will trip. Okay? Now, let's move on. Electron affinity. Alright? I said we did not cover this trend. It is the energy released when an electron is added. Is that right? And, alright, it becomes more and more negative as it's added to the nucleus. You're adding an electron. I'm looking at helium. I'm looking at neon. I'm looking at argon. I'm looking at krypton. They all have zero electronegativity. Why?
Because they don't.
They have the full 8 electrons. They don't like the added one. Is that right? So, noble gases have zero electronegativity. Let's look at one more set. Beryllium magnesium, calcium, strontium, barium, and then why do they have zero electronegativity? They have an S2 filled orbital. Yes or no? Do they like the incoming p orbital? Like it gives them partial half-filled stability. Is that right? So, alkali earth metals also have zero electronegativity. Alright? Now, which are the ones that are really, really high? Which are the ones that love their electrons? Halogens. They're one short. Is that right? They're desperate to get that electron. So, halogens have very high electronegativity. Let's see. Here is an exception. Nitrogen and zinc and manganese. Why do they have zero electron affinity? What's nitrogen's electron configuration? P3. What is manganese? D5. What is zinc? D10. What is cadmium? D10. They are in their half-filled or fully filled electron configuration. Do you think they welcome the incoming electron? They don't. Alright? Electron affinity pattern is electron affinity increases across a period and decreases down the group. That is the general trend for electron affinity. Do we understand this? Okay. I think I finished my notes here. Is that right? That's the last of my notes. All right. Let me stop